right, so today we're going to probably hopefully finish up on stacks and queues and list-based data structures in general. We started talking about stacks last time, which were a LIFO data structure. A LIFO data structure is a last in, first out data structure, so that it's like a stack of dishes. You put something at the top and you take something off the top. From that perspective, stacks are what are called a restricted access data structure. So if you contrast this with other things that we've seen before, for example, collections like lists, sets, right? These are a bit unstructured. Right? In that lists, yeah, do have a little bit of structure in that there's a first element, the second element, third element, fourth element, etc. Sets are unordered, but that's it, right? They're really unstructured. They just hold stuff. Right? Lists are ordered, but not necessarily sorted. There is a difference between sorting and ordering. Order means that there's a first element, the second element, the third element, etc. Just making sure that this works. Sorted means that the first element is the first element. So 1, 2, 3, 4, 5. And if it were 3, 4, 7, 2, right, that's ordered in that 3 is the first element and 2 is the last element, but it's not necessarily sorted. You can impose an ordering, right? Sorting imposes an ordering on the list. But you can't sort a set. Why? Because a set is unordered. But you can impose an ordering on a list's state, right? A stack imposes an ordering, or a structure, I'll say, structure on the behavior, right? You are only allowed certain access to certain elements, right? That's why we call it a restricted access data structure. If you have a stack, you can only work at one end, the top. You can push stuff on and you can take stuff off, but that's it. That's its structure. It's through its behavior, through its publicly facing interface, not on the underlying elements, right? The basic functionality is that, of course, you can create a stack, but otherwise you have a push, right? Add an element to the top of the stack, and again, it's just for visualization purposes. Top, bottom, it doesn't matter. You can always flip them around. You have a pop, right? Remove and return the element at the top of the stack, right? Okay? So let's go ahead and take a look at a really quick implementation here. Let me go ahead and come over to Eclipse here and create a new class called myStack. Right? And I'm going to immediately parameterize it here so that it can be a stack of integers. It could be a stack of plates. It could be a stack of doubles or strings. Right? So let's go ahead and decide how are we going to implement this stack. Well, if I go to my object-oriented programming principles, right, Going got 4 principles there. I've got inheritance and abstraction, I've got encapsulation and abstraction, right? Those are going to be necessary. But I've also got polymorphism. I've already got that, right? It can hold anything. It's parameterized. What about inheritance? What if I reused the implementations that I did over here with, say, a linked list, right, which implements my list? What if I reuse those? What if I extend my linked list? There we go. Remember that this puts it into an inheritance hierarchy that defines an is-a relationship. Is a stack a list? Is a list a stack? Do either one of those relationships sound correct, right? Remember over here, where this is a restricted access data structure. We should only have a push and a pop operation. Otherwise, it ain't a stack, right? By implementing or extending my linked list here, what have I done? I've inherited all these methods, including, say, add element to the end, or add an element to the start, or replace an element at an arbitrary location. Does that sound like a stack of dishes to you? It doesn't to me. So I'm not going to do that. I'm going to abandon that object-oriented programming principle because it doesn't make any sense. Right? It does not follow an is-a relationship. Maybe the other way around. Maybe a list is a stack. That sounds even less right. So I'm going to rely on another object-oriented programming principle that we covered, right? Composition, private list of integer, whatever, right? Elements, okay? Now, at this point, I'm abandoning my, my implementations over here, my linked list and my array list, in favor of Java's, right? So I'm immediately going to say, nope, you're all done. I'm going to go ahead and start using Java's lists, right? Because why reinvent the wheel? They're so much better anyway, okay? That's composition. So we've got this stack data structure. Inside of it, we've got a list data structure. It owns an instance of a list, just like your store class owns a person, which is a manager. Manager owns an address, which is an address, et cetera, right? Composition, it's composed of other objects, okay? I'm going to go ahead and have a public my stack, right? And I will have no argument constructor here. Elements is equal to new. Ooh, what kind of a list should we have? Should we have an array list that we're already familiar with? Or might we want a linked list like we just covered? And again, I'm abandoning my implementations in favor of Java's implementations here, linked list. Well, let's think about that. I'll go ahead and leave it as a linked list here for a second, and we'll come back to it, right? And the implications of it. I want to get this done. I just want to have a public t pop, right? Return something, and a public void push, where we take an element of type t and we add it to the top of the stack. So let's go ahead and document these two things. First of all, I'm just going to make this compile so that it returns null. What does this do? It removes and returns the element at the top of this stack. All right. Well, what does this one do? Push. It adds the given element x to the top of this stack. All right. How do we do those in terms of the underlying list here? In fact, if you want to, you can call this the underlying list. There's a list inside of here, right? I'll go ahead and leave it as elements, though. Right? If I'm going to push, let's think about pushing first. If I've got a list, right, and it's initially empty, does it matter where I put it at the beginning or the end? Nope. Center, there is no center, right? So where do you want to put it? This dot elements dot add, where? At the end or the beginning? Let's go with the end, right? Why? Because, well, that's the first one that popped up. But if you're going to push it at the end of the list, so if there are 5 things in there already, and you're pushing it at the end of this list, then what's the orientation of your stack? This is the top, right? Normally a list is going to be depicted horizontal. Now we're looking at it from a vertical perspective. And if this is the top of my list, the end, right, then where would I pop from? Return this dot remove, or dot elements, dot remove from an index. What index? 0? That's the beginning. I need to work at the other end, which is what? This dot elements dot size. Careful, if there are 5 things in there, 0, 1, 2, 3, 4, minus 1. That's it. That's all there is to it. I've got an underlying list here that I'm treating as a stack by always working from one end. But take a look at the outside world here. If I create a my stack of integers, I'll call it s, is equal to new my stack of integers. Right? And I push, right, 10. I push 20, 30, 40. 20, 30, 40. Am I able to arbitrarily add it at any location? S.add at index, right? Index 3, and I'll add 42. Right? Can I do that? No, why? Because I've protected it from the outside world. That underlying list is private, right? And I have protected it from the outside world by only giving you this push and this pop operation, making it a restricted access data structure, okay? But I didn't have to reinvent the wheel. In fact, everything here was in terms of the other list, right? All that functionality, I retain that functionality, but I don't lock myself into that inheritance hierarchy where it doesn't make any sense. A stack is not a list and a list is not a stack. All right, wonderful. Let's go ahead and, if we push, 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 let's go ahead and pop, 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 pop. System.out.println s.pop. and I'll do that 4 times. What should the output be here? If I go 10, 20, 30, 40, then what's the first thing out? 40, 30, 20, 10. In other words, reverse order. Okay? Awesome. What if I do one more? Push 4 things, but pop 5? What's going to happen? Index out of bounds exception, a linked list. What the hell is a linked list? I'm working with a stack. Should I know anything about linked lists? Should I know anything about indexes or indices? Right? No. So why is it telling me about this stuff? Right? It's because it's a leaky abstraction. What behavior do you want right here? You've got an empty stack. What do you expect to come out of it? Nothing? All right, well, what's nothing in Java? Null? Okay. So, if this stack is empty, return null. Help me write that code. Gee, I wish I had a functionality that told me that it was empty. That seems like secondary functionality that would be really helpful. Okay, if it's really helpful, then do it. Right? Public Boolean is empty. What's my condition for being empty? If this dot elements dot size is 0. That expression there. If it's 0, then it returns true. It's empty. If it's not 0, then it returns false, and so it's not empty. Right? Maybe I misspoke there. Right? So if this stack is not empty, great. Now I've got a functionality to do that. This dot is empty. If it's empty, then we'll go ahead and return null. Reformat everything. Run it. Wonderful. Now I'm not getting a leaky abstraction anymore, right? It's not leaking information that, by the way, under the hood over here, we've got a linked list, right? Okay, great, cool story, right? Who cares, right? I don't want to have to care about that. The whole point of abstraction, the whole point of encapsulation is so I don't have to worry about that crap. Right? What's an alternative? If this is empty and you try to pop off of it, I'm going to go ahead and give you null. What if I, in fact, pushed null at some point? Are you going to be able to distinguish between those two outcomes? Right? So, for example, exactly the same run here, but it's completely different behavior because you actually put null into the stack at some point. How do you know that what you pop out is null because there was an empty stack versus what you pull out, it was null because you pushed null at some point? Maybe that's an argument that we don't want to support null values. So we could come in here and say, if we don't support nulls, right? If we don't want to support nulls, then if you ever try to push null, or if x is equal to null, right? Then what can we do? Well, here's one option, no op, noop, which is no operation, just simply return. Silently. Okay, that's great. I'm not going to do anything about it. And I'm not going to tell you that I didn't do anything about it. Right? What's another option? Maybe a little bit better option. If you give me something bad, I'm going to do what? Throw it back at you. Throw a new illegal argument exception. This stack does not support nulls. Okay. Now over here, when I try to put in null, now I get that a message that says this stack does not support nulls. Right? That's not a leaky abstraction. It's everything is in terms of that stack. Okay, now it's null. It's definitely null because it was empty. We could have done the same thing up here though. Right? If it's empty and we try to pop from it, we could instead, as an alternative, throw a new illegal state exception. You cannot pop from an empty stack. Right? And so trying to do that results in a meaningful exception that we can then try and catch and then deal with somehow. Right? Two options: return a flag value, let them deal with it, or throw it back at their face with an exception and then let them deal with it. Okay? There's no one right answer here. In fact, we'll see that both of them are right. No operation? Okay. Throw an exception? Okay. Right. What if you tried to push on to a full stack? Right. So think about where you've seen full stacks before. The call stack. Function calls function, calls function, calls function. When you've got runaway recursion, for example, right, and you just have a never-ending cycle of function calls function calls function, right? What eventually happens? Your stack frames will be at full, and that's only like 4 megabytes at most or something like that, right? So when the stack is full and you try to make one more function call, what happens? What happens to a glass of water when you fill it up and then you keep trying to pour water into it? Overflow. And that's called a stack overflow, right? That's where we get that, that's where they got that, the name for that website, right? Yay. All right, so do we have that problem here? If we've run out of memory, we're pretty much screwed no matter what, right? But we could design a stack that had a capacity, a maximum capacity. Private, int, max capacity, right? And we'll go ahead and say that it's, by default, it's 100, right? We could then have another constructor here that took in that max capacity, right? And this dot max capacity is equal to that max capacity, right? That has me thinking that maybe we make the default 0 as a flag value to indicate that there is no maximum capacity. But if you gave me a maximum capacity of, say, 5, right, then I could check that. Right? So let's go ahead and say, go over here to the push out and say, else if this dot is full. Right? If we've got a full stack, then what we'll do is we'll throw that back in their face. Illegal argument exception. Right? This stack is full. Right. Now, what is full? It's going to be very simple, similar to is empty, right? Is full. But the first thing we do is we check, has that capacity been set yet? If this dot max capacity is not equal to 0, right? If it's equal to 0, then it can never be full, right? That's just our flag value to indicate there is no capacity, right? Just use a regular old stack. If it's not equal to 0 and this dot elements dot size is equal to this dot max capacity, then I will return true. Else return false. It is full. Is there a way that I can simplify that? If this expression is true, return true. If the expression is false, return false. Just do what then? Return that expression, and you're done, right? Don't write code like a first weeker or something like that. There, that's much better. All right. There is no capacity here, so we could keep going as many times as we want. For int I equals 0, I is less than 100, I plus plus. Right? We'll go ahead and s dot push. Right? Push I. There we go. And now we're getting 99, 97, or 98, 97, 96, 94, or 95 out. Right? If we had specified that there's a maximum capacity of, say, 3, then the second that we push that 40, it gets full, right? And we throw that this stack is full. Lots of bells and whistles that we could add to this thing here, right? Beyond the core functionality of push and pop. Right? That's the optional functionality. The nice to have functionality, right? What happens when you pop from an empty stack? Throw an exception, return a flag value, right? How do you impose a capacity? An optional capacity, right? How do you even implement a stack? Right? Well, how did we do that? Over here, I chose to use a linked list, which is probably the best choice. Why is this the best choice? Let's take a look at the implementation of Java's linked list. Hey, it's keeping track of the first element and the last element. In other words, the head and the tail. It's keeping track of the size, just like we did. Oops, I lost my place. Right? And let's take a look at the nodes, right? It has a node class. What does it look like? A next and a previous, as well as the element that it's keeping track of. What does that tell you? What kind of a linked list is this? It's a linked list that's keeping track of both of them, and it is a doubly linked list. You can traverse that way or that way. Right? Jumping to the middle is still difficult, though. Because of that implementation, this is very, very efficient. If you work at one end, whether or not it's the head or the tail, it doesn't matter. It's going to be efficient. Putting stuff here and taking stuff out and removing does not involve any shifting whatsoever. What if I change this to an array list? There we go. Array list, array list. Import that. Good, done. Right. What's going to happen now? Not much, because I'm always working from the end and from the end. So we already saw that that was efficient with respect to an array list. What if I had decided different? What if I had decided to say add element at the beginning, 0 and 1? There, I forget what the actual method is, but what if I had done that with an array-based list? Shift everything over just to accommodate this one. Take it out, pop it off, shift everything back down. I don't want to do that, right? Because I know that that's inefficient. Undo, 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 undo. There we go. Right? So a linked list is a perfect implementation of this. One other operation that you might want to consider is what's called a peek operation. You've all peeked at your presents before you've opened them, right? Maybe not, maybe you're good. Basically it means return, but do not remove the element at the top of the list. You could very easily just pop it off. Okay, I see it, I've got it, great, now put it back on, push it back on. Right? That's why it's an optional functionality. But let's go ahead and implement it. Public t peek. Right? Right. I'm not going to remove it, so this dot elements dot get the element at the top of the list, which would be this dot list or elements dot size -1. There we go. Return. Now be careful. Are you going to be able to peek on an empty stack? Nope. So to do error handling. Decide how you're going to do that. That is a wonderful stack implementation. Now let's look at its brother, which is a queue. Right? What is a queue? A queue is a line, right? That's just regular old speak, right? It's more British, like you queue up. You don't get in line. What do? You queue up. You get in at the end of the line, right? And it's a FIFO, which is first in, first out data structure. Right? No line jumping. Right? In other words, if you get in the line and there are people in line already, you are getting at the end of the line. We usually depict that horizontally. Here's my queue. You go in one direction, and sometimes you can call that push. Mostly it's called offer. For now, I'm going to call this NQ. Right? NQ it. And then it comes out the other end. And for that, I'm going to call it DQ it. Right? So it's just like a line. If you want to be served at Dunkin' Donuts, you get at the end of the line. Right? People are served at the other end. And you wait your turn, and you move ahead in the line until you're there. That's why the first one in is the first one out. Okay? Now imagine how we're going to implement this. We want to work at both ends. So what's it going to look like? Undo, undo. Come on. There we go. New class queue. T. There you go. My queue. I should have done that. Guess what? I'm just going to steal the exact same ideas as over here. I'm going to use a list In fact, I'm going to use a linked list. Public queue. You can do the capacity on your own. This dot elements is equal to new array list of elements of type T. That doesn't sound right because if I'm working at both ends, I can see a lot of shifting going on. Right? So definitely want to go with a linked list. There we go. Import that. And what is my implementation going to look like? Public T DQ. Return. Does it matter which end we work at? Right? Do we work at this end and put stuff in here and take stuff out here, or put stuff in here and take stuff out here? Well, if you want to be consistent with our picture, which end do we work at? We enqueue it, we dequeue it from where? This dot elements dot the end, right? Dot get or remove this dot elements dot size -1. There's the end. Public void enqueue tx. This dot elements. If I'm working at that end to remove stuff, where do I put the stuff at the other end? The beginning. Dot add at a particular index 0 x. There. I won't get fancy with all the bells and whistles. What would it look like? Virtual cut and paste stuff. Instead, I'm going to change this to a queue. And I'll call it queue instead. And get rid of all this. Q.enqueue 10, 20, 30, 40, 50. Yeah, just 4. There we go. Q.dequeue, that thing, right? 4 times. Because again, I don't have any error checking here. I haven't decided how to deal with that. What order would these come in and what order would they go out? 10, 20, 30, 40. 10, 20, 30, 40. Right? First in, first out, just like a fair line at Dunkin' Donuts. Right? Dunkin' Donuts is the only one I know on campus, so. I don't know. Are they busy enough to have lines? Yes, no? Okay. I don't know. I don't drink coffee, so I don't know. Anyway, there's no line jumping. Again, it's a restricted access data structure, and you have the same things as before. On enqueue, insert something at the end of the line. Dequeue, you remove something from the front of the line. You have the same exact options as before. Same exact considerations and options as before. All right, cool. So there are some variations here, right? You could support the you could of course support the arbitrary removal option, or general options, I should say. General options. You could support the arbitrary removal of elements, right? So you get in the line, it's taking you too long to get your coffee at Dunkin' Donuts. What do? I've got to get to class. I leave. Right? We could support line leavers. Right? You could allow arbitrary insertions. You could allow line jumpers. Right? VIPs, very important people. Right? Okay, they go to the head of the line because they've got the gold coffee ticket from Dunkin'. I don't think that they do anything like that, right? But they get to come to the head of the line because they're very important, right? Or they paid extra at Disneyland to jump the line, right? And everybody pays extra to jump the line, and now the lines are just as long as before, right? Right? So you could have line jumpers here. That's called a priority queue. Priority queue, right? Allows you to define priorities and insert elements at a location such that the elements are served highest priority first. For example, the classic example here would be running an operating system. Right? So let me go ahead and show you what's running on my personal computer right now. Right? OBS is certainly at the top. And just like yesterday, OBS, the front end, is claiming that it's only using 7.9% CPU, but that is indeed a lie, right? It's using 129% of my CPU here. And that's why I've got the hot plate here, because it gets very hot. For some reason that there is a Windows server, no, it's not Windows server, it's a Windows server at the other top. And I've got a whole bunch of other stuff running here. Not everything is running at once, right? The operating system is handling all this stuff and saying, all right, you can run now. All right, you need to go to sleep now because somebody else needs to run. I've only got 8 processors here, maybe 16 with hyper-threading. Only 16 of you can run at one time. So I'm going to manage you all and give everybody an equal amount of time. There's a little nice utility called nice, right? Where you can designate that I'm going to be a little bit nicer, right? That person sitting in the line at Dunkin' Donuts saying, no, I'm not that important. Go ahead of me, right? You can adjust that over a range of -20 to 20, the lowest, right? So no, I've got the lowest priority. You keep going ahead of me, right? I'll wait my turn when nobody else is busy or is being served their coffee, right? Or you can be one of those line jumpers and say, nope, I'm the most important person here entirely. So I'm going to go ahead and jump to the head of the line here. Doesn't always work if everybody says that they're the most important person, right? But as far as an operating system is concerned, yes. I mean, there are clear judgment calls here. For example, operating system stuff necessary for the running of the actual system. That should have high priority. That database backup that runs at midnight when nobody's using anything, that's the lowest priority. If somebody comes in and needs to use the system, okay, we'll go ahead and bump you and give them priority. Right? That's a priority queue, a job queue where you define that you don't want not everything is created equally. Right? Okay. You can also have what's called a double-ended queue or a deck. And in fact, this is the solution, right? Why is this the solution? Because you can get everything that we just talked about in one package. The Java interface deck, and this is pronounced deck, right? D-E-Q-U-E. It's a double-ended queue in that you can work at both ends. You can insert and remove from this end. You can insert and remove from this end. Why is this the best of all worlds? Well, because if you only do it in one end and out the other end, you're treating your deck like a queue. Great, no need for a separate implementation. If you work at one end only, put stuff in and take stuff out, then that means that you're treating it like a stack. If you do a combination of everything, right, then maybe that there's a utility in that as well, and we'll talk about that here in a moment. But otherwise, what kind of implementations are there? An array deck. What do you think that is? An array-based list. There's a linked list. What do you think that is? Exactly what it says, a linked list. And these other two are thread-safe versions of it. Let's take a look at the documentation. If you want to work at the first element, the head, then insert, remove, or examine, peek, right? You have these 6 options. Why would you need 6 options for 3 operations? Well, what happens when one of those corner cases happens? If you want it to throw an exception for bad operations, then you use add first, remove first, get first. If you want to return a special value like null, you use offer first, pull first, peek first. Likewise, if you want to work at the other end and you want it to throw an exception when you remove things because it's an empty queue, you use remove last. If you want it to return a null value instead, you would use pull last. Right? Offer, pull, add, or remove. In other words, everything that we just covered as far as stacks and queues, one-stop shopping here with a deck. Right? You can treat it like a queue, you can treat it like a stack, and you're done. Right? And it's an interface, so if you want an array-based implementation, there you go. If you want a linked list implementation, there you go. Right? Everything all in one. Wonderful. So again, in practice, don't create your own. You use the Java deck. Right? Sorry, go over there. Right? Don't create your own. You use what's provided by the language or a library. And in Java, you just need one thing, a deck. And that's it. There are priority queues. We'll talk about those later, though. Right? What about applications? Applications of stacks. One that we're already well familiar with, for example, is call stacks. Right? You're not necessarily going to use that for call stacks, but that is an application of a stack. Right? Storing breadcrumbs. Right? So Hansel and Gretel go into the forest. They're led into the forest by their parents and left for dead. Right? Hansel or Gretel, maybe, they were smart about it. They took some bread with them. Why? Because they wanted to find their way out of the forest. What did they do? They took off little pieces of bread and left them behind them so that they would know where they were. If you go from A to B to C to D, what kind of a data structure would allow you to keep track of where you've been? Oops. If you went from A to B to C to D, how do you backtrack to get out of the forest? Pop, 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 pop. Right? That's exactly the same thing as a call stack. If you have function A calling function B, calling function C, calling function D, and you return from those functions, how the hell do you get back to where you came from? Pop, 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 pop. You're keeping track of the entire way, of everywhere that you've been. You can go through the maze. You can backtrack a little bit, but not all the way to the end. Try a different path. You can still backtrack to that one or all the way back to the beginning. Lots of graph algorithms will use these. For example, DFS. DFS graph algorithms. Right? These are depth first search. We'll use this, but we'll use this with respect to trees later on. Right? You can simulate recursion using a stack. Don't abuse that small little call stack that's only 4 megabytes. The vast majority of recursive implementations of algorithms are not actually recursive. Right? They might use recursion up to a point, but they know that they don't want to abuse that small little stack space. But if you create an in-memory stack, like we did over here, this is a queue, but we did a stack earlier, now you're on the heap. The heap is a whole hell of a lot bigger. Right? It's not just limited to 4 megabytes. Now you can simulate that recursion without actually paying for the recursion and abusing that call stack. Right? You can do a lot of backtracking or optimization algorithms. Like I said, if you go down a maze, right, maybe that maze is representing some sort of a solution. Okay, well now we got to a point where, okay, this is not feasible anymore. Let's backtrack and try another solution. Try another solution, backtrack, try another solution, backtrack, try another solution, until you've found the best possible solution, or you just get sick of trying, and that's good enough, right? Those are what are called heuristics, right? What is better than good? Good enough, right? Anybody with a UP background, Union Pacific? Anybody know what the shunting yard is? Well, big giant train cars, right? You can't just take them around and move them around. What do you have to do if that car is going to San Francisco, that car is going to Chicago, that car is going to New York? I need to split them up, right? You can't just pick them up and put them over there. What do? You back them up into a shunt, right? You cut them off, then you move that part out, right? And then you move another part back in, hook it up, and move it out. Well, what have you just backed into? That shunt is a stack, right? The last one in was the first one out. So you have to be careful about how you're breaking apart your loads in the shunting yard, right? And you'll experience this in your I believe next week in your lab. No, in a couple of weeks in your lab for an application of stacks, right? What about applications of queues? So you go to YouTube, maybe you're on YouTube right now, right? And you start watching a video, right? And a little bit of the video loads, not the entire, you don't have to wait until the entire video loads to start watching, right? Just a little bit of a time. Now now it doesn't load it all up either because, maybe you get sick of the video and you leave. Well, why did we just send you all those megabytes of data? So it only has a little bit of a forward, right? What is that thing called? No? A buffer? Right? So things come in one end so that they're processed in the exact same order. What does that sound like? A queue. How do we implement a buffer? We implement it using a queue. So that data comes in at the end is processed in the same order. This is a perfect example of what's called a consumer-producer scenario, or a consumer-producer's pattern. And I'm just going to go ahead and use the picture from the book here, where we've got a bunch of producers. Think of them as web server requests, right? Where we've got thousands or millions of users that are hitting reddit.com or whatever, right? And those requests come in. We can't process them all at once, right? Because we don't have enough consumers. We don't have enough threads or web servers or whatever your resource is that are handling these requests. So we put them into a queue and let them wait. These consumers come along and say, okay, I'm ready for the next request. I will take that off of the queue, and I'll go ahead and handle that request and serve your web page or whatever. Right? This allows everything to be asynchronous. You could have, at times, you could have 5 producers coming in. You could have 1 million producers coming in. At times, you could have fewer resources, and so only one consumer is available at the time, and then 50. Later on, like we've got more resources, so now there are 50 consumers that we can handle. Now we can handle 50 concurrent requests. How do we handle all this stuff so that we make sure that none of these requests are dropped? We put them into a queue, something called a blocking queue. A blocking queue is more thread safe in that, suppose that a consumer comes up to the queue and says, all right, I'm ready for my next request to handle my next request, but there's nothing there. Right? There are no producers. So what does he do? He just sits there and says, okay, I'm ready, right? Waiting until finally a request comes in. Okay, I'm ready, now I'll go ahead and take that. Does it sound like that's pretty annoying, right? Somebody's sitting there, I'm ready, what have you got for me? I'm ready, what have you got for me, right? At that point, you give them some busy work so that they leave you alone. We don't do that with a blocking queue. A blocking queue says, shut up. Literally, they say, shut up. They put them to sleep, right? That's what threads, that's what we say when we put a thread to sleep. Go to sleep, I'll wake you up when we have something for you to do, right? When something does come into the blocking queue then says, wake up, I've got something for you. Here you go, right? The first scenario that I described was what's called busy pulling. You're always asking, is there something for me to do? Is there something for me to do? Is there something for me to do? You're busy about it. You're wasting resources asking a question when the same answer is going to be over and over and over again, no, no, no. So we put you to sleep so you're not wasting resources. You're not actually running. Right? You're in the background in memory, not active. So only the blocking queue is actually doing the work and saying, all right, now you need to wake up and go off and do your thing. Right? And this gets into another class called operations research. How do you know that you have enough consumers for enough producers? Because if you have a lot of producers and a small number of consumers, guess what? This queue is going to get very full very quickly. People are going to wait a long time to get their service, and maybe they drop out, right? Maybe that request to a web page, Reddit doesn't load, right? Oh, perish the thought, right? I have to actually go and do something productive now, right? Suppose that you have the other end, where you have a lot of consumers, but no producers, very few producers. Then what do you have? You have a lot of threads sitting there doing nothing, a lot of wasted memory, a lot of wasted resources. And if it's busy pulling, then it's super wasted resources. So this nice little balancing act, right? It gets into something called queuing theory, right? And in which case, producers come in at some predetermined or statistical model like a Poisson distribution or something. Now, exactly how many consumers do we have to employ in order to ensure that the waiting time is acceptable? The waiting time that we don't lose a customer, right? This goes back 100 years. Right, because think about an old school bank where people physically go and and there are a bunch of tellers there, and there are a bunch of producers or customers. Exactly how many tellers do we have to? What's the minimum number of tellers that we can get away with hiring and paying in order to service all the customers that are coming in? We don't want to waste them, right? We don't want to pay 50 people when we only need 5. But also, we want to make sure that all the customers are coming in and being served in an appropriate amount of time. This gets into queuing theory and what is that equilibrium, right? With respect to modern server management, right? Having redundancy, having enough servers to hit peak times, right? When when the new episode of Mandalorian is released, you're going to have a whole bunch of people hitting your servers at once. Are we going to be able to maintain that, right? You don't always just think about, well, what's the average, right? Because during those peak times, it's all going to fall apart. This gets into this consumer producer pattern. In the other class, or in one of the other sections, if you want to take a look, I can post it later. But it gets into resource pooling or connection pooling. For example, don't think of these producers and consumers or these requests. Don't think of them as requests. Think of them as a resource. Say, a database connection. Right? The most expensive thing you can do with a database connection is to make that connection and close that connection. So what if we didn't close it? Right? Now, close your resources. Right? If you are going to go with a full pattern like this, then maybe you have an argument for not closing your resources. But that's only if you're going for like the bonus, or just creating a connection factory is enough. If you wanted to, you could have a blocking queue where we open up, say, 10 connections. Right? And we're not going to pay to open up 10 more connections. What we're going to do is we're going to put them inside this queue. This queue is now our pool. Right? It's a pool of resources, shared resources. Now when one of your functions or methods needs a connection, they don't open their own because that's expensive. They go to the pool and say, can I check this out like a library book? Right? Thank you. They don't close it because that's expensive too. Once they're done using it, they give it back to the pool. They put it back into the queue so that somebody else can use it. If there are no connections at that time, right, because they're all being used, then the blocking queue says, all right, go to sleep. I'll let you know when there's one available. Right? Nobody ever closes them, nobody ever opens them, and so we're not it's way more efficient. What happens when we open up too many? Right? Then you have the same queuing theory. Do we have too many producers, not enough consumers, or vice versa, or whatever? Right? And it can be a very, very nice pattern to follow. Generally, you would use a library to do this, though. Right? A connection pooling library. All right. Any questions? And by the way, why do we use a queue instead of a stack for this? If I have 5 connections or so, right? And somebody checks it out and checks it back in, checks it out, checks it back in, checks it out, checks it back in, right? What about these 4 connections right here? They're never used, right? 4 connections, right? Go ahead and put them in a queue so that they're being cycled through and no one connection is doing all the work. Right? You're load balancing it. Right? All right. We'll get into algorithms and algorithm analysis starting next week. Have a good weekend.